Okay, let's have a look at another step 3 question. And the question I chose here is about linear transformations, which is a really important topic. You know, if you're doing mathematics in university, this is a good question to try. Right? Linear transformations are really important. Okay, let's have a look. So the plane pi, big pi, has a equation r dot n equals 0, where n is a unit vector. Fine. That is just to clarify the notation, right? This is let P be a point with a precision vector x, which does not lie on plane pi. Okay, show that point Q lies on pi, and that PQ is perpendicular to pi. Okay, this is quite trivial, right? Just do what you're told. Again, so lies on pi, right? So how do I prove that it lies on pi? Well, you chuck it in, right? You chuck it in. So x minus x dot n n. Okay, how do I do this? This becomes what? Dot n, right? Dot n. Okay, that's what we have to find. What does that equal to? That equals to x dot n minus x dot n n dot n. Right? And what is n dot n? 1, right? 1, because n is a normal vector. N dot n is just a mod n squared, right? But n is a unit vector. So this is x dot n minus x dot n, i.e. 0, right? Which means that it does lie on the plane. Lovely. And that PQ is perpendicular to pi. Okay, so dot product equal to 0, right? Classic approach. You know, what is PQ? Well, you just go x minus, what is it? X minus the position vector of Q. So you could find PQ, right? X dot n times n. Fine. Now what's this give? This is just x dot n n. Okay, well, it's a multiple of the normal vector, right? It's a multiple of the normal vector. X dot n is just a constant, right? So that's why it's perpendicular to pi. All good? Okay, let's go into the main bit of the question. Let transformation T be a reflection in the plane ax plus by plus cz equals 0, where a squared plus b squared plus c squared equals to 1. Show that the image I under T is that, and find images of j and k under T. Okay, this is just reflection. I mean, you sort of learned this in A-level already. A cleverer way might be to think about this, because you know that the normal vector is what? The normal vector of this plane is just ABC. That's the normal vector of the plane. So you might want to use that, but if you can't be asked, then that's also absolutely fine. That's also absolutely fine, yeah? But let's try to use that. So we want this, right? We want to make this point. So I have 1, 0, 0 minus 1, 0, 0 dot ABC times the normal vector ABC. Right? This is my Q. This is my Q. Right? And what do I want? I want PQ. PQ is what? How do I do this? PQ is just, well, x dot n times n, was it? Right, so x dot n times n. 1, 0, 0 dot ABC times n. ABC. Okay, which means that this is what? A squared, is it? A squared, and then AB, and then, how do I do this? AC. Yeah? Okay, so I'm saying that, well, let's say I have a plane like this. Then what happens is that, well, I have a point here, which is 1, 0, 0, and I have a point on the plane, which is Q, and I know what this vector is. I know what PQ is. Right? Okay, that's QP, by the way. Sorry about that. That's QP, by how I defined it. That's QP. Okay, so I know that it's there. So if I want to find a reflection, okay, look at my picture. If I need to find a reflection, what is this? This is equal to this, right? So what do I need? What do I need then? Well, I need P, which is 1, 0, 0, minus 2 lots of A squared AB AC. We get the idea? Because it's a mirror, right? You sort of learned this in A-level already. You know, I'm sure I don't need to explain it properly, really. Then what does that give? Well, 1 minus 2a squared, what is that? That's just b squared plus c squared minus a squared, isn't it? And then I have minus 2ab minus 2ac as required. Okay, this is just simple A-level vectors. I'm not gonna go through it in detail. Okay, now, and you do the same for J and K, okay? And it's probably symmetric in some way, all right? Now, write down the matrix M, which represents the transformation T. Okay, so from what I'm seeing, I think you're gonna get symmetric stuff, okay? So, probably for J, if I were to guess, that's probably minus 2bc, isn't it? Minus 2bc, and in the middle is a squared plus c squared minus b squared, and this is minus 2ab, right? Hopefully the guess is correct. And k, same thing, right? By same logic, minus 2a, minus 2bc. Second bit is minus 2, ac, yeah? And the last bit is a squared plus b squared minus c squared. Okay, so write down the matrix M, which represents the transformation T. Well, then, this is what matrix satisfies. I have three things to satisfy, right? And this is a 3x3 matrix, so the matrix uniquely determined. And I know the transformations of IJK, so I could just copy the rows, right? I mean the columns, right? This is b squared plus c squared minus a squared. I could just copy it. What's the next one? The J, minus 2bc. A squared plus c squared minus b squared, and then minus 2ab, right? And I don't have space for the k column. You could copy the k column in there yourself. Yeah? We all understand why the matrix M, we could just copy it, right? Because I, J, and K are the three unit vectors in the 3x3 space. So if you have a transformation of those, you could just copy them into columns. Okay, now part two. Part 2 is trivial, right? Represents a reflection in a plane. Find a Cartesian equation of the plane. Well, you just have to equate things and then solve, something like 3 equations, 3 unknowns. Okay, find your A, B's, and C's properly. Then you'll be done. Yeah, and then chuck it back into the ax plus by plus c set equals 0 in part 1. All right, now 3 is really interesting, I think. The matrix N represents a rotation. Rotation through angle pi about the line through the origin, parallel to ABC. Okay, let's draw a line. So I'm saying that I have a point here. What is the rotation through angle pi? Well, i.e. reflection, right? i.e. reflection, fine. So I have a random point. Now, why does part 1 exist? You have to learn from part 1. You learn from part 1, right? So let's consider point 1, 0, 0. It doesn't matter. And well, I know this thing passes through the origin. So let's consider a point here on the line. Well, what sort of coordinates does it have? Lambda times ABC, right? Because it's parallel to ABC, it passes through the origin. Fine. And we know that this is a perpendicular, right? Because I want a reflection along a line, essentially. You always find a perpendicular of that, right? Okay, so how do I find the lambda that I desire? Well, then I go, what is this dotted line? Is 1 minus a lambda minus b lambda and a minus c lambda, right? Okay, so then I dot it with a, b, c, and I need that to equal to 0. I need that equal to 0. Okay, then you could tell me what lambda is, right? You would be able to find what lambda exactly is. So a minus a squared lambda, this is just pure algebra, right? Minus b squared lambda minus c squared lambda equals to 0. And you see that lambda equals to a, which is beautiful because a squared plus b squared plus c squared equals to 1. Okay, if lambda is a, then I know that, what is this dotted line? I know this is 1 minus a squared minus ab and minus ac. Okay, and this is in which direction though? In this direction. Okay, pointing to the 1, 0, 0. Is it? Yes. Okay, good. So, how do I do this then? So well, what is the reflection that I decide? This is minus 2 lots of 1 minus a squared minus ab minus ac. And what have I got here? This becomes 2ab, 2ac, and what is the top? The top is just, what is it called? A squared minus b squared minus c squared? Is it? I think so. Yeah. Okay. So, you spot that this is actually just the reverse or the negated version of part 1, isn't it? It's literally the same thing, but in the minus version of it, right? And for J and K, it's going to be the same, right? You just check it for this, and you check it, 0, 1, 0. You check it, and you also check it for whatever it is, right? I keep on moving the thing. Yeah, good. Now, 4 though, identify the single transformation, which is represented by the matrix NM. Okay, so what would I try to do here? What would I be trying to think about? Well, I know that these things are sort of the negated version of each other, right? So I have multiple approaches I could do. I could either multiply NM themselves together, which might take some time, or you could note that one of them is a reflection in a plane, and one of them is a rotation through some sort of line. Okay, and remember, I'm doing M first, okay? Because M is behind, so I'm doing M first. Okay, now I imagine a general point now, okay? I imagine a general point. Now, I reflect it in a plane first, okay? And then I rotate it, along some sort of line. Now, what does that exactly do? This is actually quite an interesting thing to think about. So, okay, maybe a picture would help here, I suppose. Suppose I have some sort of plane here, okay? Some sort of plane, which passes through the origin. Okay, let's say the origin is here. I don't know. Okay, let's say I have a point here. Now I reflect it along the plane, so my point is probably down here. And now I have some sort of line here, right? Which is that line in part 3, and I rotate it in some way. I.e. here. What does that sort of do? Is that not just a reflection on this new plane? Here? Okay, my drawing is not really clear, right? But it's just a reflection here, isn't it? This has to be the same, I think. Yeah, so it's just a reflection, but in a new plane. Okay, so your job is to find the equation of that plane, I suppose, which is probably trivial. Okay, because it's perpendicular to some of the things. Then you can find the equation of the plane without any effort. All right, good. So this is a really nice linear transformation question. I like it. Yeah. Some bits I wasn't explaining very well, but I'm sure if you go rewatch it or anything, or figure it out yourself afterwards, that's absolutely fine. Okay, lots of the maths in here I didn't actually complete, but you, as long as I tell you the idea, I'm sure you could do it yourself, right? Because I don't want a video to be massive long, right? And no one enjoys me doing staring at me doing algebra anyway. So there we go.